Welcome back, and we're going to explore conformational isomers with a slightly more complicated molecule, butane. And as before, I've built molecular models of butanes. This is a butane molecule, and it's the way we typically draw it on the board in a skeletal structure or a Lewis structure with the carbons all in a row, and the first carbon is pretty far from the fourth carbon. If I have the same molecule, but there's been a little rotation about single bonds, then the first carbon can get very close to the fourth carbon, and there's going to be some repulsions there. You can see in this one, the two hydrogens are actually touching each other now, and that's a repulsive thing because there's electrons in these bonds, and when those get too close to each other, it's very repulsive and high in energy. So these two models of butane are the same molecule, it's just rotations about the single bond can bring different parts of the molecule closer or farther from each other, depending on what's going on with energies and rotations. The molecule will look different and be at different energies, but it's still the same molecule. So that's something we're going to explore, what the models look like and how we represent this on paper. And so the Newman projections for butane, it's often useful to start with the Lewis structure so it's clearer what things are attached to what and which things we're trying to draw in our representations. So butane is C4H10, simple saturated hydrocarbon. And as I draw it out, I'm drawing the four carbons in a row and placing enough hydrogens on each carbon to fulfill the octet rule. And if you counted things up, you'd see that's indeed C4H10. Now, when we go to draw the Newman projection, we sort of pick an axis to look down. And the axis that makes sense for butane is I'm going to look directly at carbon 2 and have carbon 3 directly behind it. So in the ethane molecule, there were only two carbons, C1 and C2. So we looked down that axis and looked at where the hydrogens were relative to each other. Now we're looking at C2 with C3 in back. And so if we draw the Newman projection, I'm imagining C2 right in the center there. And what's connected to C2, in the front there's going to be two hydrogens and a methyl. So I'm going to pick where to put those on the front carbon. There's the methyl, which is C1, and then the two hydrogens. Those are the things that are attached to C2 on the left side of my Lewis structure. Now, directly behind there, I'm imagining C3. But we're not going to draw it because it's hidden by C2, right? So C3 is back there, and what's attached to C3? Two hydrogens and a methyl. So I can draw this in a staggered conformation. So the carbon in front has two hydrogens and a methyl attached to it. That's C2. The carbon in back has two hydrogens and a methyl attached to it, and then they're attached to each other, and we're looking down that C2, C3 axis in this perspective drawing. And so this is hopefully clearly a staggered conformation. And what that does in this case is it places the methyls farther away from the hydrogens than they would if they were lined up. This one is a special staggered conformation because the two methyls, essentially carbon 1 and carbon 4, are as far apart from each other as possible, so they're going to be called anti. So they're anti with respect to each other, and that places those methyls as far away from each other as possible. When the two largest groups on the C1, on the CC axis, are farthest away, that's going to minimize repulsion, and that's going to be the lowest energy conformation. So the lowest energy conformation, and that's what this model represents, because you can see in this model, carbon 1, carbon 2, carbon 3, carbon 4, carbon 1 is very far away from carbon 4. if I wanted to try to visualize what that representation is showing, I would hold the second carbon, right, that's C2, and I'd try to orient it so the first carbon, C1, is pointed straight up, so it'd represent what's in that representation. So then carbon 3 would be directly behind carbon 2. So again, the shadow sort of shows me a little bit about what I'm talking about. This carbon 2 has carbon 1 pointed straight up, 2 hydrogens pointed down, and those are all pointed towards us in this molecule. So that's what we've got here. Carbon 1, carbon 2, and the 2 hydrogens that are also on carbon 2 are all towards us in this representation. And then carbon 3 is directly behind carbon 2, so it's back there. And on carbon 3 are carbon 4, which is now pointed down, just like in this picture, and the 2 hydrogens on carbon 3 are up here. So that's a good representation of what this model is representing, and it's a staggered and anti-conformation. If I go ahead and rotate around the single bond, I'm going to keep carbon 2 exactly in place, carbon 1 pointed straight up, but when I grab carbon 3, I can rotate, and that brings this methyl into different positions with respect to the first carbon. The first carbon is here. I'm starting with this anti, or as far away from as possible from the first carbon, but as I rotate around this bond, you can see that this carbon 4, is getting closer and closer to carbon 1 until the hydrogens on those 2 carbons actually start to bump into each other physically in the model, because carbon 1 and carbon 4 are very close to each other. So if I wanted to draw that sort of last conformation that I had, I would draw carbon 2 and carbon 1 exactly the way I did in the first drawing. So there's carbon 1 attached to carbon 2 and the 2 hydrogens that are attached to carbon 2. Now when I rotated carbon 3, which is behind carbon 2, it moved the methyl from down in the bottom up around to the top. So carbon 4 ended up being right next to carbon 1 and eclipsing it. And then the 2 hydrogens on carbon 3 will eclipse the 2 hydrogens on carbon 2. So when everything gets lined up like this, this is called eclipsed, just like we had eclipsed for ethane. Since the 2 biggest groups are lined up with each other, that's going to cause the most repulsion. This we're going to call fully eclipsed, and this makes it the highest energy conformation. Again, I'll bring the model up here and sort of hold it next to the representational drawing, where you can see here's carbon 2. Carbon 1 is pointed straight up. The 2 hydrogens on carbon 2 are down and towards us. Carbon 3 is directly behind carbon 2. Carbon 4 is pointed straight up, which is why it lines up with carbon 1. Then the 2 hydrogens on carbon 3 are pointed away from us and down, but lined up with the 2 hydrogens on carbon 2. So this model, the physical model of one of the conformations of butane, corresponds to this drawing, the fully eclipsed Newman projection, where we're staring straight down one of the carbon-carbon axes and trying to draw the relative configurations of the things attached to the carbons. So here we have fully eclipsed butane, and if we rotate about that single bond, which happens all the time at room temperature, these things are spinning like tops. If we sort of rotate until we capture the staggered conformation, the staggered places carbon 1 and carbon 4 very far from each other. That's more stable because it minimizes repulsions. Now, as you can imagine, there's intermediate stages. I've drawn the two methyls as far apart from each other as possible, and then as fully lined up and as close as possible. As you go about the 360-degree rotation, there's lots of other options we can draw. You can envision any conformation there as being a different energy and a different shape to the molecule. There's a couple other that are noteworthy because they're either eclipsed or staggered, just like those are eclipsed or staggered, but the relationship between the methyls, carbon 1 and carbon 4, is going to be different. So a staggered conformation is always going to be lower in energy than an eclipsed, because the substituent groups get a little farther from each other. To make it easier for me to visualize and understand, I always draw the front carbon exactly the same. So I'm thinking about looking at carbon 2 with carbon 1 straight up off carbon 2, and then the two hydrogens are going to form that sort of triangular arrangement where they're pointed towards us and down. So carbon 2 is always going to be in exactly the same place in my drawings and in the visualization in my mind. So if you look at those diagrams we talked about previously, the anti-staggered and the fully eclipsed, that's how the front of the molecule has been drawn in each one. So that's sort of my starting point for drawing the different conformations. Now I mentioned there's another eclipsed conformation where now the substituents on carbon 3 are not going to line up with the substituents on carbon 2. The first drawing we did, we put the methyl down here so it would be as far away as possible from this methyl, but those can actually be a lot closer to each other if we visualize the molecule like this and draw it like this. Now, again, orienting the molecule properly so we can see it. Carbon 1 is straight up. Carbon 2 is what we're looking at. The two hydrogens on carbon 2 are down and towards us. Carbon 3 is in back. And if I had it fully eclipsed, these guys would be lined up. That's the highest energy. Anti, they'd be as far away as possible. What I've got drawn here is where we've got a staggered conformation. Staggered, so things are not lining up, but the two methyls are fairly close to each other. They're aimed sort of in the same direction. There's little different distance between them. This relationship of having the two biggest groups fairly close to each other in a staggered conformation is called gauche. And that's a lower energy conformation, but it's not the lowest. So I usually label this lower energy because it's staggered. Things are not lining up and repelling each other tremendously, but the two big groups are relatively close to each other and interact. The other possibility is that we go again eclipsed, where things are going to line up, but rather than lining up the two methyls and bringing them very close to each other, we'll line up a methyl with a hydrogen. Over here, carbon 1 is going to line up with a hydrogen. Over here, the methyl carbon 4, which is on the back carbon, is lining up with a hydrogen on the front carbon. And then the last two substituents, as I'm calling them, the things attached to carbon 2 and carbon 3, are two hydrogens which line up. So in this molecule, again, if I want to visualize that, I start with carbon 1 straight up, carbon 2 is what we're looking at, and then I can rotate around with the back carbon until carbon 4 lines up with a hydrogen that's attached to carbon 2. So this one is called eclipsed. because things are lined up, but it's not fully eclipsed because the big group is not lining up with the other big group. Big groups are lining up with small groups. So this is eclipsed, and because it's eclipsed, it's higher in energy. Because the big groups are fairly far away from each other, it's not the highest energy. If we had the two methyls lined up, it'd be the highest energy, fully eclipsed. This one is eclipsed, but the big groups are farther away. So anytime you have an eclipsed conformation, you've got a higher energy conformation. Anytime you have a staggered conformation, you've got a lower energy conformation. And then there's different extremes. So eclipsed with big groups lining up with small groups is higher in energy, but not the highest.